let's go to a little bit of a broader view than some of the stuff that we've been talking about today and jump right into the kind of problem that we're all going to deal with, hopefully at some point of our career. I mean, we all sit here and we're all at least ostensibly interested in doing exploration for the minerals industry, and we're often presented with situations like this. We have some sort of target, in this case a geophysically defined one. We've got some red stuff, we've got some blue stuff, and really what we're presented with is a chicken or the egg kind of problem. We need to define and understand this target, and we can't understand it without knowing what's there, but how can we best optimize our drilling strategy without knowing at least a little bit of something about it? And so, like all of us, we'll define a drilling program, and depending on how much we schmoozed up here in Vancouver this year, we can hopefully get enough money for several drill rigs to start marching along some sort of pattern that we've defined based on the best geological information that we have. And so snow melts off the ground, or perhaps, the rainy season ends, and we start marching across this geophysical anomaly that we defined. So typically, we start at one end, we start marching towards the other, some sort of fence. Hopefully, we base this fence off of some sort of reality. But, we start moving. If everything goes well, the drills are moving smoothly, they start marching across, and then, every couple of weeks, you move to another hole. And so, unfortunately, everything that we're trying to do with these holes, we have to send out to a lab. In the particular location where this project was, it happened to be in Nevada, and we're looking at a 45 to 75 day turnaround last summer in terms of the assay results. And so this right here is the planned drill holes, and then you can start to see here I'm cheating ahead a little bit. This is what the corresponding assays would have been for this drill hole plan. And that first hole that we started drilling at the 1st of April, unfortunately, we don't get the assays back until the 15th of June. Then we start marching along, and then by the time our second quarterly report is due for the investors to keep everybody that we schmoozed with up here at Roundup happy, we've marched along, and we only really have, well, nothing to show for it. We're marching along this back series of holes, and we've had a couple of hits that maybe suggest that there's something there, but really we've just been skunked. And every time we start marching along a little further, we get skunked less and less, but people might not be happy. We hopefully haven't pulled the plug on this project yet, because as you can see, this is from a project that was actually a mine. And this right here is the 10 ppm grade shell, and there was actually decent grades throughout here. I mean, the two pits that this represented produced about 750,000 ounces of gold during the mine life. And it would have been great if in this hypothetical exploration program, instead of marching through and then coming back across, we could have jumped right to the section that was the meat. Both that would keep people happy who were giving us money to drill, and then also it would give us the most information about the ore body. Because in reality, that's what we're chasing. We're chasing the ore, and drilling ore and exploring ore is the best idea on how to understand your system. And so, what we're really all talking about today, and some people are going to be getting into more specifics on the details of how to perform this, but what I'm going to talk about is giving a rubric for how to perform what I like to call adaptive exploration. You can use that as a hashtag if you want to. It's a pretty good one. But what adaptive exploration is it's the ability to change how you're progressing through a project based on the available information. And that comes with a series of steps that really applies the workflow that we're all familiar with drilling and exploration, but applies new techniques and new technologies in order to use that workflow to the best of our advantage. And the main areas that you need to worry about are taking data as you're drilling, using that data in some sort of rapid analysis process that then you can also change and adapt based on new information, and then use that new information to create a targeting model that reacts and changes based on the new information. And so everything I'm about to talk about, if you think back to how things were done and how things still are done in the majority of the industry, this workflow is the same way that we've been doing it, but now you can do it in a faster, more repeatable, and more unambiguous way. And so everyone here can take a picture of this and then fall asleep or go get a coffee, because this is really the majority of what we're going to talk about. In terms of the data acquisition phase, we're going to be talking about how to structure your data properly in order to get the most out of it. And we're also going to talk about how to capture that data so you know that you're getting good data. Then we'll jump into some data processing ideas, mostly revolving around processing the data in 3D from the very beginning, modeling it and understanding it in real time, and some of the differences between real time and lagging models, and then how to leverage the strengths of different data inputs in order to create the best model possible. And then we're going to briefly touch on how to deal with the fact that we're all human beings and not, sentient robots. Well, some of us. I mean, probably you wouldn't be able to tell with a sophisticated enough robot. That's a different story. And so we'll talk about the battle royale that goes on in the minds of geologists between being right, finding the answer, and then having to deal with the reality of geology and the reality of the fact that we're all getting paid to do this, hopefully. And so first stage is data acquisition. You can't really understand things without gaining a little bit of data. And this is kind of the scenario that everyone finds themselves in. You have to report to somebody higher up, hopefully with good data. I mean, it's rare, unfortunately, that the people who collect the data are the people who are actually using the data. And so this is a little hard to read right here, but this is a drill log done at the very early stages of a career of a very young and handsome, but probably rather naive geologist who was working on that project that you happen to see that we were just looking at. And so it's a typical paper log. You capture the data, all the data is in one sheet. It's a great summary of what the rocks are doing. But you can see here there's some major structural issues, and I mean data structural issues, with how this data was captured. And so you can see here there's a column with the structural data. It's all put there. I mean, it's nice and pretty. The lines are drawn straight. They're color-coded, but it's unusable. I mean, there's really no way to pull that information of the data out and use it in any kind of refined model. In fact, how this workflow went at this particular project is that we made color copies of this, cut out the structural data, and pasted it onto a piece of tracing paper to make cross-sections. You can also see there's structural data hidden in the comments. And then also there's this nice comment down here that unravels the paragenetic relationship of some of the mineralized veins. But it's here in the comments, and it's never going to be seen again because this data was handed off to an intern who typed it into a spreadsheet, who put it into a database application, and then the comments were never read. And then, of course, we have things like abbreviations that only that geologist knows what they mean. We have qualitative data scattered around here that's masquerading as quantitative data. All these here are percentages or Likert scale 0 to 3 of mineralization intensity, which, if you happen to have your eye tuned, you can somewhat approximate, but one of the things that humans are really bad at is visually estimating volumes, and that's what you're doing when you're doing mineralization estimates visually. And then, of course, there's the fact that this paper sheet was printed out about 10,000 times and sat in a file drawer, and every time you went to log core, you got another piece. But about 2 months into the program, we realized that sphalerite wasn't as common as we thought it was, but we probably should be logging garnet. And so you cross out sphalerite, you write that it's garnet, you put that down, but then unfortunately nobody changed that column in the database. So for another month after that, we thought that there were places where we had 10% sphalerite, which wasn't the best idea. So this is an example of a more recent project, unfortunately not logged by that young, handsome geologist, but by a team of excellent geologists that we've had a chance to work with at Oriented Targeting Solutions recently. And you can see here, it's a much better data structure. It's got a place for all the data, and all the data is in its proper place. So the data, it's uniformly categorized. Everything in it is set in a way that when you say something in it, when you use an abbreviation, that's what's there. The standardization even applies to the comments. So they have a set grouping of when you see this is how you describe it with these words, so it's queryable. We have metadata. So here's a column on the quality of the orientation data that went into this, a topic that my colleague Chris Brown is going to be talking about more here shortly. And then you can see here, this is one of the more useful things that we like to recommend people to do, is that the vein mineralogies here isn't buried into the comment. You see here, it's basically a true-false table. So you can pull out in your modeling and your understanding all the veins that contain pyrite, all the veins that contain chalcopyrite, all the veins that contain quartz, in a simple true-false table for ease of modeling and understanding. And so you see down here, each one of these tabs is a place for different kinds of data. You have a lith log, you have an alteration log. You don't have alteration mixed in with your lithologies. You don't have numeric data mixed in with your text data. All these suggestions are basic data hygiene that every database should really accommodate. And then of course it does have accommodation for those happy accidents where, say, you all of a sudden discover that you should be logging garnet and not sphalerite. There is a place where you can use the geological observations that we're all trained to make and use those as long as you have some sort of standardization that you're using in order to keep everybody on the same page. And one thing you will notice here is that there's no qualitative data. There isn't a 0 to 5 scale on the amount of pyrite that's logged here. That is in a different place. It's understood to be qualitative, and then it's supplemented with more quantitative ways of understanding that information. And so capturing the data itself, there's a number of different data streams that are sort of best practice, but then really are designed to give you a full picture of what the geology is doing. The first one is, remember, we're trying to capture this in real time, and so necessarily avoiding those assay lab difficulties is in-field geoanalysis. That's using things like portable XRF, portable XRD, infrared spectroscopy, as well as a field portable comminution and sample preparation circuit that gives you the best sample that you can possibly present to each one of these in-field instruments. And actually, there's an example of which sitting over here in the corner, if anyone wants to take a look at it. It's the system that Reflex has developed with a little portable crusher and jaw mill. I had a chance to use this equipment over the summer. Great for producing samples that give you the kind of sampling integrity that you need to perform rapid analysis on them. And then, of course, there's the structural data. Structural data being near and dear to my heart as a structural geologist. The structural data, it needs to be data dense. You need to target the data that you're capturing in order to understand what you're looking at. A lot of the data sets we work with, they'll measure 300 fractures, but really they're interested in the veins, and they'll measure 2 of those. So the structural data that you're capturing, it has to be targeted to what you're trying to answer. It has to be categorized properly, so everything from logging the thickness of the structures to logging the mineralization of those structures. As much information as you can capture, the better, because then you can put that in and understand what geologists do best. And so instead of spending all the time arguing over the core bents, oh, well, I think that's 0.5% pyrite. Nah, that's 0.75% pyrite. I worked on this project before, and that's what we called it. Using these 2 data streams in the proper way with a little bit of quality control added on top of it allows geologists to focus on what humans are best at. And that's looking for anomalies, that's looking for things like texture. Machine vision hasn't anywhere come close to being able to define a foliation in my experience yet. And looking for patterns, looking for those things where the details inform the larger picture. And so all this information, in order to use it in a rapid manner, has to go into a data repository. And hopefully that data repository has been structured properly to accommodate the data that you're putting into it. And so this kind of quality capture and in-field geoanalysis, when I talk about this with people, a lot of them jump and say, it's like, oh, no, that's too new technology. I trust the assay lab more. Well, unfortunately, this kind of thing has been around for a while. If you come over and take a look at the Reflex equipment, here is the first iteration of it from 1910, a tiny little jaw crusher, a benchtop ring mill that were used in a gold mine in California. And then, of course, understanding structural geology in 3D from the beginning has been around since the 1830s. Here's a nice cross-section of Switzerland as a block diagram. That's how structural geology really started. But the issue with why things aren't done in 3D to begin with really comes down to the fact of data processing. And so everyone here might have heard the term of garbage in, garbage out. So no matter how good you are at cranking away internally the geology and the model, if you put crap in, you're going to get crap out. And so hopefully with properly structured data and an understanding of how to capture that data from multiple streams and put it into a single place where you can actually work with it, you're not going to get garbage out. So you put science in, but now the problem is some of us might come in across people who have the garbage can in their brain. Well, not you, Chris, not my boss. And so science in, but in a garbage way of understanding it gives you garbage out. And so going through data processing, starting out with understanding that each of these geological systems are in 3 dimensions, I start my work with a simple mantra, and that's geochemistry is what's there, and structure is where it's going. And for some of you out there who like rocks more than geochemistry, I will make the argument that pretty much everything you see in a rock, alteration, lithology, really is just geochemistry in different ways. But we could talk about that over beers. But so starting with that mantra, a lot of people go into really modeling in what's 2.5 dimensions. And that's that method that we used at that project that I was working on very early in my career, where you take geochemistry coming in from whatever source, whether it's in the field or from a traditional assay lab, and then you have to extrapolate that data. You have point data, and then you're trying to understand what it does in 3D space. And then so the geologist then will take what they see, and because it's complicated, they'll use some interpretation. They'll say, well, this foliation means this underground. And so that goes in. And then with the structural geology data, well, structures are complicated. Rocks are never a simple Coulomb fracturing system where you have these beautiful X-shaped stockworks. If you do happen to see that, good for you. But most of the time, the world is a little bit more complex. So the structural nature of the rocks that we're looking at has to be simplified, and then that all gets put into something that I had a geostatistics professor, he called it geopoetry, where it's a good idea of maybe what's going on, but really it relies on a lot of interpretation and things that aren't quantified and codifiable in order to understand what's going on. And so really, everything should be working towards the idea of developing a model in 3D to begin with that is as close to reality as possible. And so that means working with all the inputs that we just talked about, geoanalysis that's done rapidly in the field, with hands-on geology, with geologists who are working on things that geologists are good at, and then dense structural data in order to give all that information a direction. And so this is something that everyone maybe has seen before. It's the cyclical nature of the exploration workflow. You go from the data repository into a way to look at that data and visualize it. Unless you happen to be a really sadistic person like me, a spreadsheet isn't really the nicest thing in the world to look at. So systems to visualize that data, especially geochemical data, structural data, programs like IOGAS, are the best way to understand and to start using those human traits of pattern identification and the other things that we're good at in order to understand that data and figure out how best to model it. And so the modeling and understanding of that data is born directly in 3D. Ideally, I like to use Leapfrog myself. There's other 3D options out there. But there is no generating cross-section step where you generate these things, you create interpretations first, and then you put it into the model. Because that's a separate layer where errors can come in, and then they get hidden because when things are in a 3D model, our natural tendency is to take that as gospel. And unfortunately, then those models, which may have layers of qualitative information and layers of interpretation put onto it, are then used to deploy the drills, which may or may not give you the proper data. And so the cycle continues. And so what we're really trying to do is take this exploration workflow cycle and make it into the scientific method, where you make an observation, you develop a hypothesis, you test it, and then the key thing is to change the model based on the tests. And that's something that, unfortunately, is the last step that doesn't often happen in geology. And so really creating that model, which then you can test, you have to rely on the strengths of your different data inputs. And so geochemistry and geology logging itself really tell you, again, what's there. So geochemistry has the power to remove ambiguity. If anyone has happened to log multiple intrusive phases with argillic alteration in them, it could be almost impossible to visually tell apart one intrusive phase from another. Really a good way to do that? Take a look at the geochemistry. So a lot of times it'll show up in ways that you never thought would be distinctive enough to really log. The other thing that geochemistry gives you is pathways. It tells you where things are moving around. I mean, all ore deposits are really the story of one element moving from one place and being put into another place. Geochemistry can define those pathways. And then geochemistry, a lot of people say that it will give you vectors. What it really gives you is gradients. It will tell you where things are in a high concentration and where things are in a low concentration. Unfortunately, that's not a vector. A vector is a magnitude and a direction. And so what gives you the actual direction, part of the vector, is the structural geology. And so structures themselves are often the targets. They form the pathways that the geochemistry is moving along. And then they give you the direction. If you're drilling a fault, it could be a big deal if the fault's going this way and then you think it's going that way, so you drill that way, but then you miss the fault. And so that structural information gives you the third dimension. And so you combine that with the stuff that good geologists will contribute, and that's defining parameters for the model, understanding the geology, domaining, understanding it at different scales, taking things like mineral foliation and stretching lineations that are a millimeter scale and using that to understand a mineralized system on a kilometer scale. That's something that, unfortunately, automated systems can't really do. And that's the key input that a geologist will make in an exploration program. And then, of course, there's the reality check. One of the arguments that I get a lot when people see that we're using software like Leapfrog that has implicit modeling functionality in it is that you put all this data in and then it spits out a thing, and the thing that spits out is like, I've never seen a geology thing that looks like a blob. Like, that doesn't happen. Well, that's because the model wasn't properly parameterized and you just wanted the machine to do the thinking for you. And so that's the key part in this workflow, is having the geologist be the understander, and then all the data coming in is being the thing that they're using to understand. And so the next step that a lot of new things are coming onto the market now that allows us to work with is that the ability to collaborate on these kinds of things. And so there's really two parts in that, doing the collaborative science. And so there's that old saying that the person who sees the most rocks wins. Well, the corollary to that is the rock that sees the most geologists will probably pay off. And so we've had a chance, and a lot of these projects I've only been to once or twice, or I haven't been to at all, but I've been able to work on projects just in the past year at all those locations with teams of geologists that both make me a better geologist because I'm understanding what they do and learning from them, and hopefully I can bring my own expertise into their project to give them a new perspective. And the ability to share data, especially data that is well organized, is incredibly important to that process, because when you send a data set to somebody else, they have to work with it through their own filter of biases and interpretation. And so having the data well organized and well categorized means that the data itself can be moved around to different people to have their input on. And then, of course, the modeling step is collaborative now as well. I think someone had mentioned something about Leapfrog Central. And I analogize that as kind of like GitHub for geological models. It allows people to have different inputs, to test different hypotheses, and to work together, as well as the fact that you can use it as a way to put that data on somewhere and do some modeling and not have to have a huge server rack in a tent out in Alaska. And so that's the general rubric of what I'm calling adaptive exploration, and hopefully a lot of people in this room are saying, well, Geoff, that seems pretty obvious. Why are you standing up here talking about this? You know, why can't we just get to the coffee break a half an hour sooner? Well, the fact is that it's here already. There's an example of the infield geoanalysis setup right over here in the corner. Really fun to play with. Just grab some gravel from out front and start crushing it. It's kind of cool. And then, of course, the other thing is that drilling technologies are rapidly changing to the point where you can drill at a much faster pace. And so there's really no sense in having rapid analytical technology if all of a sudden you have to wait for the drill to do things. So there's been a couple of outfits in Australia who've developed some really cool drilling technology that allows you to drill faster, safer, in the same ways that you can deal with, you know, an RC hole. It'll pull a hole in the ground just as quickly. So there are companies out there who are working on these technologies right now. But unfortunately, we live in a situation where the people who are going to be implementing these technologies are really only human. And so this is an anecdote that I like to tell. If anybody's ever heard of electronegativity or electron orbitals, you can thank this guy, Linus Pauling, for having to memorize that in high school. So he's one of the most distinguished chemists in American history, two-time Nobel Prize winning chemist. And he happened to have a student called Dan Shechtman working in his laboratory. And so Dan Shechtman had an idea that was inspired from non-repeating tiles in traditional Islamic art about quasi-crystals. And so in his trying to understand the fact that there can be crystalline structures that are not necessarily periodic, working with Linus Pauling in a rather famous and public setting, Linus talked about his students' research as there's no such thing as quasi-crystals, only quasi-scientists. I mean, anybody here who's been through the graduate school system might find that as kind of disappointing to hear from your advisor. Well, Danny boy over here wasn't really dissuaded, and so he ended up being right, and discovered quasi-crystals, and which have implications from everything from battery technology to high-temperature superconductors. And he, of course, won the Nobel Prize for it, despite what his advisor told him. And so really what a lot of the geology that we're trying to figure out comes down to is whether or not the people making the decisions find it to be more important to be right and to prove the model that they already have, or to find the answer, which means necessarily changing that model that we have of our information based on new information. And that ability to kind of change your mind on the fly is something that is difficult for a lot of people who are born and raised as scientists who have a lot of self-worth wrapped into knowing the answer, really find it difficult to do. And so then, of course, there's the other human fallacy, is that dealing with complex situations causes us to shut down a little bit. Dealing with complicated geology forces us to make simplifying assumptions, which in reality, that's what any scientific model really is. And so dealing with large amounts of data, especially data that can be disorganized and problematic, the more complicated it becomes and the more problems in the data acquisition and the data processing, you start to see things like this and you're like, I don't know, just drill a hole, man. We'll see what's there. Which sometimes you get lucky, but science isn't about luck. And so really, this adaptive exploration process that I've outlined here is here already. There are companies using it in various degrees in various parts. And it really comes down to a quote that I like from a guy called Helmuth von Moltke the Elder. Great Germanic name, but he was the leader of the Prussian army before the First World War. And they've known this for a while, that his quote is, "No plan of operations extends with any certainty beyond the first contact with the enemy." But I left that out because, geology. So, and he was right. Armies operate like this all the time. Geologists, unfortunately, don't. We will march straight through the anomaly, straight into the jaws of bankruptcy, because that's what our model says. And so what it really comes down to is that we need to devote resources and time to developing a good data structure so that we can put good data that we've taken ownership of acquiring into a structure that allows us to develop a model that we can change and inquire into and test based on collaboration and based on new information. And so that kind of rubric is really where we're going. And hopefully that'll take us into the future, but the future really is right now, and that's what we're sitting in, is a room of people who believe in this kind of future.